So as you can see, I moved to the Technical University of Munich. This is the clock tower, which is the symbol this year because it's the 150th anniversary of the Technical University. And I will tell you something that has basically very little to do with what we have heard so far. But in the end, I will use some waveguides also to excite magnetic systems. So it's half the beast, if you want. So I will talk about a system that we have studied for quite some time. And I always thought that how many years can you study exactly the same system? But we recently made a lot of progress in designing the interfaces. And we discovered some new effects that I will talk about. So this is only light blue because I will skip over this very briefly and then show you some results that we obtain using spin-orbit ferromagnetic resonance. I will show you how we can detect anisotropic Gilbert-type damping in these systems. And then finally, we can also control the spin-orbit fields by voltage. Of course, none of the work has been done in Munich. All of the work has been done in Regensburg. And the main drivers were Lin Chen, a postdoc who has been working on this subject, and Martin Decker, who is now a postdoc, and Robert Islinger. And there are a lot of other people that worked on the subject, in particular also the group of Dominique Boujard, where we get the 3-5 materials, Jaroslav Fabian, who gives us theory support, and Dieter Weiss. I have a long-standing collaboration with him. And funding comes from the DFG, and Lin is funded by the Humboldt Foundation. All right, so I have to give a very brief introduction into spin-orbit fields. And I will do this by just showing you this very old paper by Bitchkov and Rashba. And what you can do is you can imagine you have a semiconductor system with broken structural inversion symmetry. So for example, you can have an asymmetric quantum well. And if you have such an asymmetric quantum well, the charge density of electrons or holes will be shifted to one side. And this produces an electric field. Now, you have this electric field, but nothing happens to the system unless you start moving electrons. Then the electrons will see this electric field, and because they're moving at relativistic, in a relativistic environment, you can express this electric field by a magnetic field. So you can rewrite the Hamiltonian. You have the charge carriers here, and you get an additional term which represents this electric field now in terms of a magnetic field. And what you can see here now, you have linear terms and momentum that couple to the spin of the system. And that's the main ingredients. And because Jairo is one of the organizers, I also put this figure from his paper here. So here you can see an example. These are these spin split shifted bands in such a Rashba system. And you can see if you look that spin is always shown here in red and momentum is shown in green, that electrons moving to a different direction, to a particular direction in the semiconductor have the spin locked to a certain direction. And typically we are lazy, so we don't draw both parabola, but only one of them. Okay, so that's a k-linear term in the Hamiltonian. You can have different k-linear terms in the Hamiltonian. You can also have a bulk asymmetry, and then you will get Dresselhaus type terms. All right, so this has been realized quite some time ago. So this was the first paper where you actually use this effect to switch the magnetization. This has been done in single crystalline material GaN manganese arsenide, and it's a bulk system. And you see the sun-like structure with these current leads here. And now you can route the currents along different crystallographic directions, and you can directly see the torques that act on the magnetization, and you can actually observe switching in such a device. And then some years later, it has been shown that if you use these planar heterostructures, so in this case it's a platinum layer with a thin cobalt ferromagnetic layer and aluminum oxide on top, that you can use a current that you run through such a platinum device to switch the magnetization in this perpendicularly magnetized cobalt film. And this was in the beginning related to Rashba type effects, but also spin Hall effects, and now it seems to be more a spin Hall driven system. So this is a polycrystalline material, but it's an interfacial effect if it's Rashba, and it could, of course, also be bulk if it's a spin Hall effect. And then there was this paper recently by Chiara, who just arrived, I saw, which was on this material nickel, manganese, antimony, which is produced in Würzburg and has a very low damping, so it's very nice to use ferromagnetic resonance type techniques to study this system. And this is a single crystalline material, and here you could see that you actually get effective spin orbit torques also at room temperature. So what we study is this system, and so as you can see, it's a single crystalline system, and it's also everything happens at this interface between iron and gallium arsenide. So the system looks like this. This is a top view on the gallium arsenide surface, and you can see the size of these spheres tells you the layer. So the topmost arsenic is a little bit larger than the next arsenic layer, and this is the topmost gallium layer. So we're terminated with arsenic atoms, and they bond to the iron, which actually fits perfectly on this crystal if you rotate it by 45 degrees. And as you can see, there's anisotropic bonding. So the iron likes to bond to these arsenic atoms here, and there are some missing bonds in this direction. So you can immediately see that these two crystallographic directions are not the same. And that's the reason for all the physics that we see. So we get a C2V symmetry from this surface, and this is what we see in all our transport or the ferromagnetic resonance results. Now, this system has been studied by a theory group in Regensburg for quite some time. So it's the group of Jaroslav Fabian, and they did ab initio calculations, and the important message here is that what we look at is the interfacial system. So it's the spin orbit field that is imprinted onto the iron single crystal by the underlying gallium arsenide. So it's the gallium arsenide with the C2V symmetry that imprints the interesting physics, the spin orbit fields, onto the iron layer. And so you can calculate the band structure. This is a 3 monolayer of iron on a slab of 9 monolayer of gallium arsenide, and of course it depends on which interfacial atoms bond with which iron atoms, and you can then derive the bands that come from the arsenic or the gallium, and their spin character. So here it's shown as up and down squares. Now what they did then is they deduced spin orbit fields from their ab initio calculations, and the most general way you can write it is something like this. So you have a spin orbit interaction Hamiltonian that gives you some k-dependent field here, this W, and it links to these Pauli matrices. And if you look at this, then you get, you see that the C2V symmetry from the gallium arsenide interface imprints both a bulk inversion type asymmetry and a structure inversion type asymmetry onto the iron system. So I will talk about Dresselhaus and Rashba-Soff, so the bulk inversion asymmetry and structure inversion asymmetry, but it's not really what we understand in semiconductors for bulk asymmetry and the structure inversion asymmetry. It all comes from the interface. And if you now look at this, these spin orbit fields, you can see they lie in the plane. And now you can do some simplifications. You can go low in energy and close to the gamma point in the Brillouin zone, and then you will see something like this, so like this figure 8 type spin orbits coupling. And what is plotted here is the strength, so this W and the absolute value, and the vector field. So these are little arrows that you can see, and you can see that there's a strength that shows this figure 8, but the direction is plotted here in these vector plots here. There's one interesting thing, actually. If you switch the magnetization in the iron slab, you can also switch the spin orbit fields in some cases. Now, you can also do this for different energies. So you can go higher up in energies, and you can see from the calculations, you will see that there are higher contributions. So it's not simply a twofold, so this figure 8 shape anymore, but you now have these spin orbit butterflies. And here you can see they actually don't change direction when you switch the magnetization, but this one does. And what you see is that you always get the C2V symmetry, no matter what you do. Now this is at the interface, and now you can use this Hamiltonian, and as I said, you can derive some Rashba-like and Dresselhaus-like torque, spin orbit field, sorry. And they would look like this. As I said, I will only plot one parabola. So here, this would be the spin direction for the Rashba type. This would be the spin direction for the Dresselhaus type. And these are the corresponding Hamiltonians that are k-linear, as I said. So if you run a current through the device, you will produce this magnetic field. And this magnetic field can then, of course, interact with the magnetization. And you have two different coupling constants here. the Rashba coupling constant and the Dresselhaus that describe the strength of this interaction. All right, so this has been seen a long time ago, actually, and this was a painful experiment. What has been done here is there is a single crystalline iron gallium arsenide structure, and then in this paper they had to thin down the gallium arsenide to produce a tunneling barrier. So you have to remove the whole wafer and hope that you don't get a pinhole somewhere. And finally, they realized this thin gallium arsenide tunnel barrier. They put a gold electrode on top, and then you can rotate the magnetic field. So there's and measure the tunneling magnetoresistance. And this has been done before with gallium manganese arsenide also. So now you have tunneling through this junction with only one ferromagnetic electrode, and the TAMR that you get looks like this C2V symmetry. And this is actually the theory developed by the group of Fabian. And what was interesting is if you now change the bias field, so from minus 90 to plus 90, you can actually see that you indeed flip the direction of the C2V symmetry. All right, so it shows this pronounced C2V symmetry. And you can show furthermore that you need both Bitschkov-Rashba and Dresselhaus terms at this interface to produce this effect. If one of them is gone, then there is no TAMR. All right, then we did an experiment that looked like this. So we take again a gallium arsenide bulk crystal. We deposit iron in situ, so we move the sample without breaking vacuum into an adjacent metal MBE, and we put these iron layers on top of monolayer thickness. 4 monolayers of iron are just ferromagnetic at room temperature. And then we cap it with MgO and aluminum oxide. And then we produce these hall bars here. And since we want to compare crystallographic directions for the same structure, we use this bent structure here. So we have different crystallographic directions where you can send the current through on the same device. So we measure lateral transport, and what we then do is we measure the in-plane anisotropic magnetoresistance. So we rotate the magnetic field. Now, if you look at this slab in ab initio calculations, you can see, so this is the gallium arsenide, these are the iron layers. So you have a few iron layers here, and you can see at the interface something special happens. And what I plot here is the density of the electrons contributing to transport, so this is rho. Then this red dashed line is the anisotropy in the density, so along these two different crystallographic directions. And then this blue curve here is actually the magnetic contribution to the anisotropy. All right, so then we do the AMR measurement. So we rotate the magnetic field. We do it for a different device here. We rotate the magnetic field. And then we can plot the AMR as a function of direction. And everything happens at this interface. So if you do so for a very, maybe we go back one. So if you want to have this density of electrons dominating, we need to obviously make a very thin iron layer. So if you do so, you can indeed see that you see in the crystalline contribution to the anisotropic magnetoresistance, you see the C2V symmetry. If you go slightly thicker in 6 monolayers, you can see these two lobes don't have exactly the same height, but it's almost 4-fold symmetric. And if you go to 8 monolayers, the C2V symmetry disappears. So it's an interfacial effect. It comes from this anisotropic charge density at the interface. And this is in fact a temperature dependent, so this is also interesting. So the C2V symmetry changes as a function of temperature here. But I don't want to talk about this one. So we see this C2V symmetry, and again it reflects the interfacial spin orbit fields. All right, so now we set out to do spin orbit FMR, and now we're running a current through such a device. So I plot this Rashba type field, and if nothing happens, if we don't send the current, there's also no spin accumulation. The same for the Dresselhaus type. Now, if we run a current, we displace the Fermi surface here. We can see now we have a net spin accumulation that builds up. So we have a spin accumulation in the y direction, which is proportional, of course, to this coupling constant here. And the same happens here. In this case, you get a negative spin accumulation along the x direction if you run a current along the x direction. Okay, so something happens And now we can run a high frequency current through the device, and we get a high frequency field, and this high frequency field, of course, can drive the magnetization into resonance if we use the correct conditions. And this has been shown in these two publications. So here's a gallium manganese arsenide bar, and you can run the microwave current through this bar. And what happens then is that the current density creates the spin-orbit field inside the sample. The spin-orbit field drives the magnetization. And then if the system has anisotropic magnetoresistance, you get a resistance that varies with time. And then you get a mixing voltage that you can easily detect. So it's a very simple experiment. So you just need a bias T, a voltage source bias T, and a voltmeter, and you have a device where you run the current through. It's a bit tricky to get all the spurious signals out, but in principle it's a very simple measurement. And then what you of course do is you sweep a magnetic field until you reach the resonance. So this is what we did in our device. So it's a 5 nanometer iron gallium arsenide film. It has strong crystalline anisotropies. That's important actually. So if you apply the magnetic field along a certain direction, which is defined by this field angle phi h, the magnetization does not necessarily follow in this direction. It might lock into this direction phi m. So only at infinitely strong fields, you would also always have the same direction for field and magnetization. And of course, in the easy and hard axis, the magnetization follows the field direction. So when you then measure this voltage here, and you sweep the magnetic field at a fixed frequency, then you will see this resonance line here. And you can see that this resonance line actually is made out of two lines. There's a symmetric part and an asymmetric part. And you can then model this voltage using these two Lorentzian line shapes here. So this is the width of the line, and this is the resonance field position. Okay, and from this paper we know that, well, we know this anyway, so we can get the resonance and the field line width. So that's the typical ferromagnetic resonance experiment. But from this asymmetric part, we get the in-plane spin-orbit fields, and from the symmetric one, we actually get the out-of-plane spin-orbit fields. So if you do such a scan as a function of, now you see this is phi m, so we already calculated the magnetization angle from the field angle using the susceptibility. Then you see the voltage does such a dependence as a function of angle, and here I plotted the crystallographic directions, and this is shown for this current density here. And we can now fit this using this function here. Basically what's in here is the strength of the anisotropic magnetoresistance, the current density, the length of the device, and the magnetization. And then you get these different fields here, and these are related to the Dresselhaus and the Bitschkov-Rashba contributions for such a device. And if you now plot them, so you have the Dresselhaus and the Rashba type, and then the total spin-orbit field for this particular device, which is structured along the 1, 0, 0 direction, this is the field that you get. Now you have to do it for many devices, and if you do so, you can actually map out the whole spin-orbit field of such a system in the plane. And it's all calibrated by this 0.1 millitesla field strength here. Now there's something else that I will talk about later. This is the susceptibility that you automatically measure when you measure the ferromagnetic resonance, and I will get back to this in a second. But this you actually need to convert phi h to phi m. All right, we can now compare in a more or less fair comparison with other systems. So these are polycrystalline ones. These are single crystal systems. And you can see, so without going into the details, you can see we're not the greatest ones, but we're also not the worst ones. So it's in the range also of metallic systems that you can see here. All right, now I want to come back to the susceptibility and to the observation of anisotropic damping. So what we use to analyze our system is, of course, the Landau-Lifshitz-Gilbert equation, which has this precession term and the damping term. So alpha, of course, is a fundamental parameter. And for most ferromagnetic materials, alpha is typically isotropic. And moreover, if it's non-isotropic, it is usually linked to some extrinsic effect. So you might have two Magnus scattering or something like this. And we were wondering, since we have such a low damping, so such a nice system where we can look at damping very closely, could it be anisotropic? And obviously it is, otherwise I wouldn't show it. But so what we measure then typically is this. So this is the resonance field as a function of angle, and you can fit this by using the energy landscape of the magnetic system. By this you get the anisotropy fields out, you get the G factor. These are the anisotropy, the uniaxial anisotropy fields. This is the magnetization angle phi m as a function of phi h, and the green line would give you the corresponding signal for a polycrystalline sample. But here we see we get deviations, obviously, where we have the strong anisotropy. So the magnetization cannot lock into the field direction. And now we can also measure the line width as a function of angle, and this is what is shown here. Now this fit here is using the susceptibility as a fit parameter, and you can see it fits all angles perfectly. So with one fitting parameter, which is the damping constant in this system. So you get an increased field line width, of course, because of dragging effects in such a system with anisotropies. But nevertheless, you can use the same line width to fit all the data. And now we do this for very thin layers. So this is a 1.9 nanometer film. You can see again, this is the line width as a function of angle. And you can also see that we can fit it with one single alpha. And this is what I meant. So we use the imaginary part of the susceptibility with all the anisotropies included. So H1 and H2 are the effective B and H field that you typically use in the Kittel equation. And then you can use one fitting parameter alpha to describe this whole dependence here. Now, if we go to a slightly thinner film, you can see it doesn't really work anymore. So we get a different alpha here, and we can either fit one line or we can fit another line. So it doesn't work anymore. And now if we do another comparison, let's say here, so this is again the thick sample, and we can see the hard axis and the easy axis. If you do a frequency-dependent line width, you can see they basically sit on the same line. They are fitted by one common parameter, and the zero field intercept is close to zero. Now, if you do this for this thinner sample, you can't do this anymore. You can fit this one with 0.007 and this one with 0.0085, and they basically have no zero frequency intercept, so extrinsic effects should be very, very small, but you can't fit them with the same line. And you can do this for all kinds of angular dependencies using this fitting function. And you can see you can fit all the data, but you have to vary the damping parameter. So these are just for comparison, these are the lines that are deduced from these fits, and you can see they don't fit, but for each angle you get a different damping parameter. So there seems to be an angular variation in alpha, and it's an intrinsic one because there is no zero frequency offset. All right, so we can plot this now as a function of angle. You can see for the thick sample it's basically isotropic, but for the thin one you see C2V symmetry. Big surprise. And now we can look at where damping comes from in the breathing Fermi surface model by Kambersky. And if you're in the high temperature regime, it grows like 1 over tau, so the scattering momentum relaxation time. This is the strength of the spin-orbit interaction, and this is the density of states at the Fermi energy. And remember, we've seen that the density of states, or sort of something that is related to the density of states at the Fermi energy, is anisotropic. So if you now plot this, you can see this is the alpha that we measure, and this is a rescaled density of the states at the Fermi energy. You can see it fits actually perfectly. So it's really an intrinsic effect that we measure here. So it's intrinsic anisotropic damping. All right, now finally I would come to this thing that we were glad that we finally got it published today, actually, or at least accepted. We have a very nice system here because our iron film is grown on a semiconductor, and we can produce a Schottky barrier. And if you have a Schottky barrier, we can tune the voltage across the barrier. And then we thought, okay, we know from the calculations that the spin-orbit fields as a function of energy vary, so the spin-orbit field should be tunable. So that's what we wanted to do. But first, we needed to get a measure for this. I have one side note here on, so we have at least something with Cavitronics. We can also do spin pumping in the system. So this is a very old original data by Mitsukami, where you compare a permalloy film sandwiched between copper layers. So there you pump out a spin current, but everything that you pump out comes back again. And you can see as a function of thickness, nothing happens. But if you sandwich between platinum, you can see increase of spin pumping, which is like 1 over the thickness. Now, you can extract from these measurements a contribution to the Gilbert-like damping, which is the spin pumping contribution, which contains the G factor, the magnetization, the 1 over the thickness, and also this spin mixing conductance. And it's typically somewhere around 10 to 19 or so. Now we also get a dependence of alpha on thickness for this iron gallium arsenide thickness, and it's actually not so small. So it's only an order of magnitude smaller maybe, which is actually surprising if you consider that the Fermi surface of gallium arsenide is not really matched to that of iron. All right, so spin pumping. And here I would also like to mention that we can now pump the spin out, but we can convert it here into a voltage using, for example, the inverse spin Hall effect or the spin galvanic effect or any other effect that you can think of that converts the spin current into a voltage. Now you do this by attaching a probe here. We've seen this morning. And then you can either measure the time averaged DC spin current that you pump out, or you can in fact also measure the time varying AC spin current that you pump out. And we do it like this. So now here's my Cavitronic part. We integrate our devices into this coplanar waveguide. It's not a beast, it's only a chicken, but it's only part of the system. But this morning it also looked like a chicken to me. So it's only in this geometry that, and also the perpendicular geometry, where you can actually measure the signal from inverse spin Hall effect or spin galvanic effect in a clean manner. And you can see it here. So here it's really a spin galvanic effect. And you can see the voltage actually corresponds to this expected angular dependence of the signal for the SGE. And we call it a spin galvanic effect because there's no non-magnetic conducting layer, right? So our system is sitting on gallium arsenide, and this gallium arsenide is non-conducting. So we measure really within the same layer at this interface. So now you can argue, of course, this interface neither belongs to iron nor to gallium arsenide. So it's this special channel at the interface. And again, you can compare to other spin-to-charge conversion efficiency. And again, we're not the worst ones, but it's very close, actually. All right, now we want to control the spin-orbit fields. So now we design this a little bit differently. We actually add a Schottky barrier here. And with the voltage, we can actually change the built-in field at the Schottky barrier. All right. And this was the motivation. We thought, okay, if we go to higher energies, we see that there's a change in the spin-orbit field. So we should be able to detect this. And this is what happens then. You apply a gate voltage. In this case, it's negative. In this case, it's positive. In this case, you flatten out the bands. Here, you steepen the Schottky barrier. And this is the E-field dependence as a function of voltage across the barrier. And now if you do exactly the same measurements again, so we again measure these voltage traces, you can now see that the asymmetric and the symmetric contributions change as a function of voltage. So here you can see the data traces, and you can see these changes in the shape of these Lorentzian lines. And what you can see, they actually don't even have the same slope. So you can also do the angular dependence, and you can also see this dependence if you do the full angular dependence of the symmetric or the antisymmetric voltage. Now from this you can again look at the efficiency of the change of the Rashba-Dresselhaus field as a function of gate voltage, and you can see it's -10 here and +2, and this is something that we don't really understand actually. And here is the combined plot where you can see the zero voltage spin orbit fields compared to a voltage of about -1 volts. And you can see you can really effectively tune the spin-orbit fields along some particular directions in the plane. Actually, just to mention briefly, we also see changes in the out-of-plane spin-orbit fields, which is shown here, and here they show the same sign, but also different slope. Now, we went to the theory colleagues and told them, okay, now you have calculated this whole band structure, so just extract the fields for us, and it actually doesn't work. So we're off by orders of magnitude. So the effect is much larger than what we expected from the simple band structure calculations. And we don't really know what it is, but we think that it probably has something to do with trapped states at the interface that we can load and unload with applied voltage. But it's very hard to prove this, because you would have to prove it locally. So this is, again, is the modulation amplitude shown here for the in-plane and out-of-plane spin-orbit fields, and it's derived in Rashba-Dresselhaus contributions for different stripe orientations. And as I said, it has been accepted today in a journal that I haven't heard of until the beginning of this year. All right, and with this I come to the end. So we see that the electronic properties of this very simple interface are dominated by the C2V symmetry of the gallium arsenide terminated crystal. And we can actually use this crystalline anisotropic magnetoresistance to quantify the spin-orbit fields. I haven't shown this. We see mutual charge, spin and charge conversion at this interface, so you can drive a spin current into the device or use the driven charge current to create a spin-orbit field. And we can also control these voltages of the spin-orbit fields. And these are all very large and robust effects at very simple interfaces. Actually, we were worried a bit that these interfaces degrade. This is what we know from a long time ago. But we recently remeasured the device that we have measured for the first time 3 years ago, and the spin-orbit fields are still exactly the same. So it's actually a simple but also very, well, reasonably stable interface. Thank you for your attention.